allowed you to record, you can. All right. Okay. So last time we started talking about manifolds with boundary, right? So these were spaces which had charts of two kinds, right? So either say this is your manifold with boundary. So either you had a chart near a point which mapped to an open subset of Rn, or otherwise you had a chart which mapped to an open subset of the closed upper half space Hn. Right? So this would be some open subset of the upper half space. Yeah. All right. And a point P was called a boundary point if, as in this picture, in some chart it maps to the boundary of Hn. And we saw using Brouwer's invariance of domain that if P maps to boundary Hn for some chart, then it maps to boundary Hn for any chart, right? Okay. So therefore, we could define unambiguously the boundary of N. Okay. And then notice that if phi is a chart, then by what we've just said, phi will map the intersection of the chart with boundary M to boundary Hn, right? And boundary Hn, this can be identified with R n minus 1, right? So if you put phi tilde to be phi restricted to U intersect boundary M, then this will go from U intersect boundary M. So let me call this U tilde. So this is an open subset of boundary M. Okay. And this will map to boundary Hn, but I can take it to map into Rn minus 1. So this will map to an open subset V tilde of Rn minus 1 as a homeomorphism. Okay. All right. So if I have a chart phi I from say Ui, let me put an I here everywhere. And the change of charts So these will then give charts on boundary M, you see, these phi I tildes, which are the restrictions of the charts of M restricted to boundary M. So those will give charts on boundary M mapping into Rn minus 1, right? And it's easy to see the change of charts phi j tilde composed phi I tilde inverse. This is smooth from Rn minus 1 to Rn minus 1. Okay, so this is a C infinity diffuse between open subsets of Rn minus 1. Okay, because it's the restriction of phi j composed with phi I inverse, right? And that by definition of manifold with boundary, that is smooth in a neighborhood of boundary Hn. So is this clear? This phi j tilde composed phi I tilde inverse will be smooth from an open subset in Rn minus 1 to an open subset in Rn minus 1. Is this okay?
Yes.
Yes, sir.
Okay, so what does that mean? That means that del M together with these ui tildes and phi I tildes, yeah, this is an n minus 1 manifold, right? Okay, because we have smooth charts on this mapping into Rn minus 1. And this is a manifold without boundary, right? Okay. So boundary of boundary M is empty. Is this clear? Yes?
Yes.
So this fact that boundary of boundary M is empty, this is in fact the motivation. This was Poincaré's motivation for homology. Okay, I mean, Poincaré is one of the founders of algebraic topology, and his motivation for defining homology was this observation that the boundary of the boundary is empty. Okay. So Poincaré initially he tried to define homology using manifolds with boundary, but that doesn't quite give the same as singular homology which you learn in your algebraic topology. That leads to something called cobordism theory. Okay, so that's a different. It leads to a different theory. Anyway, that's just a small remark. So now we want to define. So in this picture, at a point in the interior of M, we know what the tangent space is. It's given by derivations at the point of the ring of germs of smooth functions at that point. Similarly, we want to define the tangent space at a boundary point. So the tangent space at a boundary point should also be a vector space of dimension n. Okay. And what we want is that we also have the tangent space to boundary M. Okay. So we have, so suppose P is a point of boundary M. Yeah. Then what we want is that TPM, so this should be a vector space of dimension n. isomorphic to Rn, and we want to identify the tangent space to boundary M with the subspace of TPM of dimension n minus 1. Okay, so boundary n is a manifold of dimension n minus 1. So TP del M, this is a vector space of dimension n minus 1, right? So we want to identify this n minus 1 dimensional vector space with the subspace of this n dimensional vector space, which you can see in this picture here. This would be the tangent space to the boundary, and this plane would be the tangent space to the manifold at P. Is it clear what we want to do?
Yes.
Okay, so how do we do this? So first we have to define TPM, right? So we have to be a bit careful here because we want to again use the same definition, that derivations at the point P of the ring of germs of smooth functions at P. But normally smooth functions at P, we need to look at a neighborhood of P, right? Which is homeomorphic to an open set in Rn. But here a neighborhood will be homeomorphic to an open set in Hn. So instead what we can do is look at functions which are smooth in the sense that we defined last time. Smooth in near P means that they extend locally to smooth functions in a neighborhood of P. All right. And this is what how we defined a function on the closed upper half space to be smooth, right? If for any point on the boundary of the upper half space, there is a neighborhood of it in Rn to which our function extends to a smooth function in the neighborhood in Rn, right? Okay.
Yes.
So now we're going to define f, a function on an open subset U of M is smooth if f composed with the inverse of a chart. So this goes from a subset of Rn to R. This should be smooth. Now, this this subset is either an open subset of Rn. In that case, smooth is the usual definition, or otherwise it's an open subset of Hn. Okay. In this case, the definition of C infinity for a function on an open subset of Hn is as before, right? Locally, it extends smoothly into the lower half plane as well. All right. Okay. So now we've defined what is a smooth function on an open subset of M, a manifold with boundary. So then we can define in the usual way, if P is a point of boundary M, we can define C infinity MP to be germs of smooth functions at P. Okay, where germs are defined using pairs U comma F, such that U is an open subset of M containing P, and F is smooth on U. Okay, so smooth on U means that when I look at F composed with the inverse of a chart, that is a function on an open subset of Hn, that is smooth according to our previous definition. All right. Okay. So then we can define, as before, TPM to be the space of derivations at P of the ring of germs of smooth functions at P. Okay, is this all right? Yeah. So
Yes.
the only difference is in the definition of C infinity MP. Yeah, that's all. Okay, and then you can show that this is a vector space of dimension n. Okay, with a basis del del x1 up to del del xn, as for the case of manifolds without boundary. So I'm not going to do that. But now I want to talk about the tangent space to the boundary. So if P is a point of boundary M, so then we have the inclusion map I from boundary M to M. So this will induce a linear map, which is the derivative of the inclusion map at P, di at P. So this will be a linear map from TP boundary M to TPM. Right? What is this linear map? It's the usual way we define the derivative of a map between manifolds. So if I take a tangent vector V to boundary M, so this acts on smooth functions in a neighborhood of P in boundary M. So I want to get an element of TPM, which is going to act on germs of smooth functions at P in M. So if I take such a function F, which is smooth in a neighborhood of P in M, then I look at F composed with the inclusion. So this becomes a smooth function in a neighborhood of P in boundary M. And so then my tangent vector V can act on it. So I look at V of F composed with I. Okay. And so I get a linear map. F goes to V of F composed with I. So that defines an element of TPM. Is this okay?
Yes, sir.
Right. So now suppose I have a chart phi with components x1 to xn from an open subset U of n to Hn such that phi of some point P, phi of this point P in boundary M is a point Q in boundary Hn. Okay. So then I know that phi tilde, which is x1 up to xn minus 1, this will go from U intersect boundary M to boundary Hn, right? Which is identified with Rn minus 1. This will be a chart on boundary M. Okay. And so then del del x1 up to at P up to del del xn minus 1 at P, this will be a basis of the tangent space to boundary M. Right? Because x1 to xn minus 1, these are coordinates on boundary M. Right? So this will form a basis of the tangent space of boundary M. And if I look at the derivative of this inclusion map, this will map del del xj, which I think of as an element of TP del M. It will map it to del del xj, thought of as an element of TPM. Okay, so this del del xj, this acts on functions defined in a neighborhood in boundary M. This del del xj acts on functions defined in a neighborhood in M. Is it clear? Okay, so why is this true? It's just you just verify this because if I take a function which is smooth in a neighborhood of P in M, so I look at del del xj of F. By definition, this is del del xj of F composed with phi inverse at the point Q, right? And since del del xj, I'm differentiating in a direction which is parallel to boundary Hn, right? This is the same as the derivative of this function restricted to boundary Hn, right? So that means to restrict it to boundary Hn, what I have to do is look at F composed with the inclusion I. So that restricts F to boundary M, and then compose with the inverse of the chart of boundary M, phi tilde inverse. Right? So this will restrict F to boundary. This F composed phi inverse will be restricted to boundary Hn. Okay. And this by definition, this is exactly the derivative of this inclusion map at P applied to del del xj at P acting on F. Right? Just use the definition of the derivative of this inclusion map. Is it clear? Yes?
Yes.
Okay. So that means that this DIP, it maps the basis of TP del M, del del x1 to del del xn minus 1. It maps it to del del x1 to del del xn minus 1, which is a linearly independent set in TPM. So therefore, DIP is 1 to 1, right? So that means we can identify the tangent space to boundary M with a subspace of TPM, right? Via this derivative of the inclusion map. Okay. And the tangent space to boundary M is then identified with the span of del del x1 up to del del xn minus 1. So this n-dimensional subspace of TPM. Is this okay?
Yes.
All right. Okay. So now suppose V is a point in a vector in TPM where P is a point of boundary M. So then we say that V is an outward pointing vector at P if for some chart phi near P, the derivative of phi at P maps V to a vector W1 to Wn in Rn whose last coordinate is negative. Wn is negative, all right? So in this picture here, the vector V would look like this. And its image under the derivative of the chart would be some vector W which points into the lower half space. Is it clear? Okay. So such a vector we will call an outward pointing vector. Okay. All right. Is the definition clear? Yes. Yes, it's all right. Yes.
But is it well defined?
Yeah, so I'm just going to say now that why is this well defined? Okay, so suppose psi is another chart, right? So then I can write psi as F composed phi, where F is the change of charts. Okay, so so this change of charts by definition of manifold with boundary, this is a diffeomorphism between open subsets of Rn from V to W. Okay, such that phi p is going to be a point of V intersect boundary Hn, and psi p is going to be a point of W intersect boundary Hn, right? And the change of charts is going to map V intersect Hn to W intersect Hn, right? And it is also going to map V intersect boundary Hn to W intersect boundary Hn. Is this clear?
Yes.
Yes? Yeah,
Yes.
this look like this. But so because it maps V intersect boundary Hn to W intersect boundary Hn, the derivative of the change of charts, df at the point phi p, is going to map Rn minus 1 cross 0 to Rn minus 1 cross 0, right? Because this is the tangent space to boundary Hn, right? And boundary Hn is going to boundary Hn under F. So therefore, df is going to map the tangent space to boundary Hn to the tangent space to boundary Hn. Is this clear? Yes?
Yes.
Okay. So now,
Yes.
my what is d psi at P? It's going to be df at phi p composed with d phi at P, right? Now d phi at P maps V to this W1 to Wn. So I have to look at therefore df at phi p applied to W1 to Wn. Now W1 to Wn, here the last coordinate Wn is negative. In particular, it is non-zero. And since df maps the subspace where the last coordinate is 0 to the subspace where the last coordinate is 0, if I take a vector whose last coordinate is non-zero, then because df is 1 to 1, it will map to a vector h1 to hn, where the last coordinate hn is non-zero, right?
Yes.
Okay. Now there are two cases, either hn is positive or it is negative. But if hn is positive, so then df is mapping this vector to a vector with whose last coordinate is positive. Therefore, by the definition of the derivative, that means if I look at f of phi p plus the straight line, I mean, if I look at the straight line passing through phi p in the direction of the vector w, right? So this gives me a curve. The derivative of this curve is exactly h1 to hn, right? Yes?
Yes. Yes.
So if hn is negative, if hn is positive, then the image of this curve is going to lie inside the interior of the upper half space for t small, right?
Right. Yes.
But that's a contradiction because w is a downward pointing vector. So this is a straight line pointing into the lower half plane. And f is a diffeomorphism. It maps the upper half space to the upper half space. So it has to map the lower half space to the lower half space. So if this line goes into the lower half space, its image has to go into the lower half space. Okay. So therefore, hn cannot be positive, right? Otherwise, we'll get a contradiction. Is it clear?
Yes.
Yes.
Okay, so hn is negative. So that means that d psi p of v, this is df at phi p of w1 to wn. This is h1 to hn, where hn is negative. And so the other chart psi also maps the vector w, the vector v, to a vector whose last coordinate is negative. All right. So outward pointing vectors are well defined, independent of the chart. Okay. Is this all right?
Yes.
Okay. So now we can use this to define an orientation on the boundary of M. So suppose we have an orientation mu on M. So for us, an orientation, remember, is a choice mu p of orientations at each tangent space, right? Okay, which is continuous in the appropriate sense. So then we can define an orientation mu tilde at all points of the boundary of M, okay, as follows. So if P is a point in boundary M, then we define mu tilde P to be the equivalence class of an ordered basis V1 to Vn minus 1, where V1 to Vn minus 1 is any ordered basis of the tangent space of boundary M, okay, such that if I look at such that the given orientation on M, mu p, this is the orientation on M, so it's an orientation on TPM, mu p should be equal to the orientation given by the ordered basis n comma v1 up to vn minus 1 for some outward pointing vector n at P. Okay, so maybe let me draw a picture. It's just a local picture. So here's P. So basically I'm saying that, oh, maybe I should, no, okay, maybe I should make this a three-dimensional picture. All right, okay. So, all right, so what should I do then? I want to 3-manifold with boundary. So for example, okay, fine. So let's take the ball, okay? The closed unit ball. So this is a 3-manifold with boundary, which is S2, right? Okay. So this is a point of boundary M, P, and this is the tangent space to the boundary. All right. Now, what I say is I have an orientation on the full tangent space to M. Okay, now the tangent space to M in this picture is just R3. Okay, so I want an orientation on this two-dimensional subspace of R3, which is the tangent space to the boundary. So how do I get this orientation? I take any outward pointing vector n, and then I declare a basis of the tangent space to the boundary v1 up to vn minus 1. I declare this to be the orientation of the boundary if so this is defined to be mu p tilde orientation on boundary M if, well, if I take n comma v1 to vn minus 1. So this is an ordered basis of the tangent space to the whole manifold, right? This is an ordered basis of TPM. This ordered basis should give me the given orientation of M. So, okay, so maybe I should be more precise. This is an orientation on TP boundary M. Yeah? And mu p is the given orientation on TPM. Okay, is this clear?
Yes.
So we have to check this is well defined, independent of the choice of ordered basis v1 to vn minus 1, such that this is true, and of outward vector n, right? So if n is another outward pointing vector, so n here is in TPM minus TP boundary M. This is an outward pointing vector. So suppose I take another outward pointing vector M. And suppose W1 to Wn minus 1 is another ordered basis of TP boundary M. Such that this M W1 to Wn minus 1, this also, the equivalence class of this is also equal to mu p. Okay, so this is also equal to n v1 to vn minus 1. Okay. All right. So then this means what? So let T be the unique linear map from TPM to TPM, which sends n to m and v1 to vn minus 1. These go to w1 to wn minus 1. Okay, fine. So what does the basis, what does the matrix of this linear map look like with respect to the basis n v1 to vn minus 1? So matrix of T with respect to the basis n v1 to vn minus 1. All right, so n goes to m, which will be fine, some linear combination of these basis vectors. But now, so note that m is going to equal, so this is also an outward pointing vector. So it's going to be a linear combination of the vi's. So that is a vector tangent to boundary m, plus it has to be a positive multiple of n, right? Because m is also outward pointing, right? So this is going to be some lambda n plus summation I goes from 1 to n minus 1 alpha I vi, where lambda is positive, right? Because m is also outward pointing. All right, so we're almost out of time. Let me stop this session and start a new one. Okay. Yeah. Okay. So we have this linear map T, which sends one basis of TPM to another basis of TPM, which sends an outward pointing vector n to an outward pointing vector m, and it sends a basis v1 to vn minus 1 of TP del m to a basis w1 to wn minus 1 of TP del m. So m I can write as a positive multiple of n plus a linear combination of the vi's. Lambda is positive because n and m are both outward pointing, right? Is this clear?
Yes, sir.
Okay. Okay. So that means I'll get a lambda here, and then I'll get alpha 1 up to alpha n minus 1 here. Now the wi's, each wi is going to be a linear combination only of the vi's, right? There won't be any n component, right? Because these are all in the tangent space to the boundary. So for the other columns, I'll have a 0 in the first row, right? Yes?
Yes.
Yes.
And here, what will I have? Here I'll have a matrix A, where A is the matrix which goes from TP del M to TP del M and sends Vi to Wi for all I. Is this clear?
Yes, sir.
So therefore, now I know that since I'm assuming that these two bases of TPM, N and V1 to Vn minus 1, and M and W1 to Wn minus 1, they both equal the given orientation on TPM, mu P. So therefore, the determinant of T is positive, right?
Yes.
So therefore 0 is less than determinant T, and determinant T is equal to lambda into determinant A, right? Because this first row, all the other entries are 0, okay?
Yes.
So this implies that determinant A is positive, and that implies that the two bases W1 to Wn minus 1 and V1 to Vn minus 1, these are equivalent. Is this clear?
Yes.
So therefore, mu P tilde, the orientation on TP del M, is well defined. Is this okay?
Yes.
Okay, good. So now we can finish this first part of the notes. So now we have given a manifold with boundary. The boundary M is also a smooth manifold. And if M is oriented, then boundary M is also oriented. All right. So you can check that this orientation is continuous in the sense that we defined earlier. That's not hard to see. All right. Okay. So now we can state what will be very important for us, which is Stokes' theorem for compact manifolds with boundary. So it says, let M be a compact oriented manifold with boundary, and let boundary M have the induced orientation. All right. Then for any n minus 1 form omega on M, the integral of d omega over M is equal to the integral of omega over boundary M. Is the statement clear?
Yes.
Okay, so M is an n manifold, omega is an n minus 1 form. So d omega is an n form defined on a compact oriented manifold. So its integral is well defined, right? Yeah, because of compactness, the integral, the d omega is integrable, right? So this integral is well defined. And similarly, boundary M is also compact, and boundary M has dimension n minus 1. Boundary M is oriented, compact. So the integral of this n minus 1 form omega over boundary M is also well defined. Is this okay?
Yes, sir.
Any questions?
So in the right hand side, we are looking at omega as a form on boundary, right?
Actually, yeah. So this is the restriction of omega to boundary m, right?
Okay.
So what this means really is that you look at I star omega, where the pullback of omega
Ye-
by the inclusion map, right?
Yes,
By the
that's what I'm asking.
exactly, yeah. So yes, that's right. That's right. Yeah. But we never write it like that. We just write omega, integral omega of a boundary m. It's understood that it's the inclusion that we're looking at. Is it clear? The pullback by the
Yes, sir.
inclusion. Is this okay? Yeah. So any other questions? So in particular, if the boundary of m is empty, then the integral of d omega over m is 0. Okay. So a form of the a differential form of the type d omega is called a exact form. A form which is the exterior derivative of another form is called exact. Okay, so the integral of a exact n form over a manifold without boundary is always 0. Okay. Is it clear?
Yes.
Yes.
So, I mean, that tells you, for example, so Stokes says integral d omega over n is integral omega over boundary m. Okay. So, example, if m is closed, so closed means compact without boundary. Then integral d omega over m is 0. Okay. So a simple example is you take say m to be S1, the circle, and you take omega to be the form which is locally d theta, where theta is a local branch of the argument. Okay. So it's a local argument function. So the point is that any two branches of the argument, they differ by a constant, right? An integer multiple of 2 pi. So d theta is well defined, independent of the choice of local branch of argument, right? Yes?
Yes.
Yes.
Okay. So in fact, what will this be? Locally, this is d of tan inverse y by x, right? Okay.
Yes, sir.
Yes.
Right, so what is the derivative of tan inverse x? It is
1 by
1 by 1
plus
plus y over x whole squared. This into d of y over x, right? Yes. So this will be 1 plus 1 by y over x whole squared into, so what will d of y over x be? It's just the quotient rule, right? So, or the product rule if you like. So it's dy by x plus y into d of 1 over x is going to be minus 1 over x squared dx. So this will be minus y dx over x squared, right? Yes?
Yes,
yes,
sir.
Okay. So what do we get? So multiply above and below by x squared. So I make this an x squared on top and a x squared here, and this becomes a y squared here. All right. And all right, I just multiplied above and below by x squared. And so then this x squared is going to cancel with 1x here. So I'll get x dy minus, and this x squared and this x squared will cancel. So I'll just get minus y dx over x squared plus y squared. Okay. So this is the one form. All right. This is a one form on S1. Okay. And what is the integral of this one form? Well, I can break up, I can cover the circle by, let's say, pieces where my one form is exact, right? So, well, yeah, I'll need something like 3 pieces. So something like this. So, yeah. I just integrate from here to here and from here to here. Right. So here I can take a branch of argument which goes, let's say, from minus pi by 2 to plus pi by 2. And here it goes from plus pi by 2 to 3 pi by 2, right? So when I integrate the form here, this will be the integral of d theta from here to here. That will be just the change in theta. So that is pi. And then when I integrate here, I'll get another pi. So I'll get that the integral of omega over S1 is 2 pi, which is non-zero. Okay. So omega is not exact. All right. Okay. Is this clear?
yes, sir.
What that means is I omega is not equal to df for any f smooth function on S1. But locally it is. So it is locally exact, but not globally exact. All right. And the same example you can do in higher dimensions. But I don't remember exactly how to do it. I'll think about it and tell you. Yeah. You can do the same in any Sn minus 1 in Rn. You can cook up a similar form. Yeah. Yeah, it's so the form in if M is equal to S2, basically you cook up the following form. So I want to define its value on a pair of vectors, right? So I take the outward normal. Okay. This is sitting inside R3. The tangent space is a subspace of R3. So I can take the outward normal at any point, right? It's just the radial vector. Okay. And I say that omega at P of a pair of vectors VW. This I define to be the determinant of the matrix. So my normal vector is just P itself. So yeah, I did define it to be the determinant of the matrix P VW. Is this clear? So this is a two form on S2. And in fact, this two form on any orthonormal basis, any positively oriented orthonormal basis of the tangent space of S2 will give me 1, right? Yes?
Yes.
Yes.
Okay. So this is actually what is called the volume form of S2. So integrating this form is going to give me the area of S2. So the integral of omega over S2 is going to be 4 pi. All right. So you can try and work this out, this calculation. Again, this is non-zero. And you can show this form is closed but not exact. Okay, so, well, I mean, it's closed because d omega is 0 because omega is a 2 form. So d omega is a 3 form on S2, that's 0. So d omega is 0. Omega is closed, but not exact because the integral is non-zero. All right.
Yes.
Okay. So, I mean, of course, note that any exact form is closed because d of d alpha is 0, right? D squared is 0. So exact forms are closed, but closed forms need not be exact. All right. And so, you know, the de Rham cohomology, you know, HK de Rham of a manifold M. This is the de Rham cohomology. This is defined to be the closed K forms modulo the exact K forms. And it turns out that it's de Rham's theorem says that this is a vector space, and it turns out that for a closed orientable manifold, the dimension of the de Rham cohomology is the same as this is isomorphic to the singular cohomology with real coefficients. Okay, this is isomorphic to the singular cohomology with real coefficients. That's what de Rham's theorem says. And so, you know, for S2, H2 of S2, what is the dimension of H2 of S2? Anyone? Orkojit, Utsav, what is the dimension of H upper 2 of S2? With real coefficients, what's the dimension? Yes, what is the dimension of H2 of S2? It's 1, right? Yes, are you there?
Yes.
Yes, sir.
Okay, the dimension of H2 of S2 is 1. So this de Rham cohomology should be one-dimensional. And here we've got one form which is closed but not exact. So this is non-zero in de Rham cohomology. So in fact, H2 de Rham of S2 is generated by this form omega. Okay, this is the span of omega. Okay, is this all right?
Yes, sir.
Yes.
Okay. Anyway, we won't really be talking about de Rham cohomology, but I just wanted to say, since we're talking about Stokes' theorem, this is one of the applications. Okay, so now let's move on to the next chapter, which is Riemannian manifolds. Okay. Okay. So Riemannian manifolds. Okay, so what is a Riemannian manifold? So up to now, our manifolds, they just had a smooth structure. So we could talk about smooth functions and so on, but we could not talk about metric notions such as length of a curve. Doesn't make sense in a general manifold. So we need some extra structure to talk about, say, lengths of curves, and then things like shortest curves between 2 points and so on. So that extra structure is given by what is called a Riemannian metric. So what is a Riemannian metric? So it's a choice of a inner product on each tangent space, which varies smoothly with the point. So in more formal terms, what is it? It is a
Smooth section of the.
it's a smooth section, exactly. So you know about vector bundles and sections. You take the cotangent bundle, take its second tensor power, T star n tensor 2. It's a smooth section of the second tensor power of the cotangent bundle. Okay, so that means at each point, it is a bilinear form on the tangent space, which varies, which depends smoothly on P, and such that this bilinear form is symmetric and positive definite. So it is an inner product. Okay. All right. Okay. So that is what is a Riemannian metric. So what does it look like in a chart? So suppose I take a chart phi equals x1 to xn. So then what is my basis of the tangent space? EI is just del del xi. And the dual basis EI star is dxi, right? So I know how to write any tensor in terms of, I know what is the basis of the space of tensors. It's given by tensor products of the dual basis, EI star, right? So G, I can write as summation over ij, G of EI ej into EI star tensor EJ star, right? Yes? This
Yes,
goes
sir.
back to the linear algebra we did in the beginning. So this is what? This is sum over ij, G of del del xi del del xj into dxi tensor dxj, right? So now this G of del del xi del del xj, this is a function on the chart, right? So this function is usually called Gij. Okay, so we get an expression G is equal to sum over ij, Gij dxi tensor dxj. All right. Is this clear?
Yes.
Yes.
Okay. So because G is a smooth section of the tensor power of the cotangent bundle, this Gijs are smooth functions, right? Okay. And so G is basically the metric, the Riemannian metric is determined by this matrix Gij. So this is a symmetric matrix, right? Because G is an inner product, so G is symmetric. So this Gij is a symmetric matrix, capital G, let me call it. And this capital G is positive definite because if I take any two vectors VW in Rn, right, then what is G of summation Vi del del Xi summation Wj del del Xj? By bilinearity, this is the sum over Ij, Gij Vi Wj, right? Yes?
Yes, sir.
And this is equal to the Euclidean inner product of GV with W, right? And so therefore, the Euclidean inner product of GV with V is just G of summation Vi del del Xi with itself, right? And this is positive if V is non-zero because G is an inner product, okay? So that means that the matrix G is positive definite, all right? So in charts, any Riemannian metric is just given by a smooth matrix valued function, which is symmetric and positive definite, all right?
Yes.
So now once we have we have an inner product on each tangent space. So I can talk about norm of tangent vectors, right? And therefore, I can do the usual thing to define lengths of curves. If gamma is a piecewise C1 curve in M, then we can define the length of gamma to be the integral of the norm of the tangent vector gamma prime t. So here norm means G of gamma prime to the power half, right? Okay.
Yes, sir.
Fine. And notice this length is invariant under reparametrizations of gamma. So what is a reparametrization? So gamma is defined on an interval AB. A reparametrization means I'm going to take some C1 diffeomorphism sigma from an interval CD to the interval AB, right? And then I look at gamma composed with sigma. So that will be my reparametrized curve. It has the same image, but now it's defined on the interval CD instead of AB. So what is the derivative of gamma composed with sigma? By the chain rule, this is gamma prime of sigma t into sigma prime t. Okay. And so what will the length of gamma composed with sigma be? It will be the integral C to D of the tangent vector of gamma composed sigma. So that will be, so the norm, I'll get norm of gamma prime sigma t into mod of sigma prime t. And now I just make the change of variable s equal to, but this is dt, I'm missing a dt. So now I make the change of variable sigma t equal to s. So then this becomes an integral a to b norm gamma prime s ds by the change of variable formula from one variable calculus. And that is the same as the length of gamma. Is this all right? Okay.
Yes, sir.
Fine. This mod sigma prime t dt becomes ds, right? So, okay. So the length is invariant under reparametrization. So in a Riemannian manifold, I can talk about lengths of curves. So once I can talk about lengths of curves, then it makes sense to try and look at the shortest length curves between points, right? And that leads us to a distance function on a Riemannian manifold. So you define the distance between points PQ to be the infimum of the lengths of curves gamma, which are piecewise C1 curves joining P to Q. All right? Okay. Then we have to show that this is a metric, right? So first of all, it's easy to see this is symmetric, right? Because the length of gamma is just the same as the length of gamma bar, where gamma bar is the same curve traversed in the opposite direction, right? Okay, the same curve with the opposite orientation, all right? So that will tell you that this function is symmetric. So dpq is dqp. Then you want to check the triangle inequality. So suppose I take 3 points PQR. So I want to show the triangle inequality holds. So what I can do is, given an epsilon, since this is an infimum, I can choose a piecewise C1 curve alpha from P to Q and a piecewise C1 curve beta from Q to R, such that the length of alpha is less than or equal to the infimum, which is distance PQ plus epsilon, and the length of beta similarly is less than or equal to dqr plus epsilon. So then I just concatenate the two curves. I look at alpha dot beta. That is a curve from P to R, which is piecewise C1. And the length of alpha dot beta is just the sum of the lengths. And so that's going to be less than or equal to dpq plus dqr plus 2 epsilon. And so the distance between P and R, this is going to be less than or equal to the length of alpha dot beta by definition. So therefore, it's less than or equal to dpq plus dqr plus 2 epsilon. And this is true for all epsilon positive. And so therefore, we get the triangle inequality. dpr is less than or equal to dpq plus dqr. Is this okay?
Yes, sir.
Now we have to show positivity of this function. So we need to show that dpq is positive if p is not equal to q. Okay. So for this, we choose a chart u comma phi near p such that q is outside the closure of u, all right? And we can assume that the image of this chart u under phi is, let's say, the ball of radius 2, and we let v be the inverse image of the ball of radius 1 around the origin in Rn. So v closure is contained inside u. Okay, we're assuming that the phi maps the point P to the origin. Okay. Now look at the matrix Gij. So this is a smooth function from u to MNR. Okay. So this is, in particular, it's continuous and it takes values in symmetric positive definite matrices. And V closure is a compact subset of U. So therefore, if I take the infimum over points P in V closure and vectors V in Rn of length 1 of the inner product of GP of V with V, right, in Rn, the Euclidean inner product, then as a function of P and V, this is a continuous function of P and V, which is positive everywhere, and P ranges over a compact V closure, and V ranges over a compact Sn minus 1. So, so this is a function on a compact set, which is positive everywhere. And so therefore it attains its minimum, which is positive. And let me call the minimum epsilon naught squared. Okay. All right. So this infimum is going to be positive, right? Is that clear? By compactness. Yes. Okay. By compactness, this infimum is positive. Now take any curve gamma from P to Q, which is piecewise C1. Suppose it's defined on the interval 0, 1. Now look at, now Q is outside this chart U closure. So gamma eventually has to leave this neighborhood V, right? So let's look at the first time when you leave the neighborhood V. So let me call that T naught. So this is the infimum over T in 0, 1, such that gamma T is not in V. All right. Okay. So this set is non-empty, right? Because gamma of 1 is equal to q. So this set is non-empty, so I can take its infimum. Okay. So I look at the first time when I exit the neighborhood V. So then because it's an infimum, this gamma of T naught is going to belong to boundary V, right? And gamma of the interval 0 to T naught, this is going to be contained inside V closure. Is this clear?
Yes.
Yes, sir.
Okay. So now look, let gamma tilde be the image of this curve gamma under the chart phi. So gamma tilde is a curve in Rn, all right? Then gamma tilde of 0 is equal to 0 because phi of p is 0. And gamma tilde of T naught, this belongs to Sn minus 1, right? Because boundary V maps to Sn minus 1 under my chart phi. Okay, remember phi was chosen, V was chosen so that phi of V is equal to the unit ball. So phi of boundary V is equal to the unit sphere. Okay. So therefore, gamma tilde of T naught belongs to Sn minus 1. Okay. And gamma tilde of the interval 0 T naught, this is contained in the closed unit ball. Okay. So now if gamma tilde of T has coordinates x1t to xnt, then we know that gamma prime of T is equal to summation xi prime T del del xi. And so the norm of gamma prime T squared, this is going to be summation gij of gamma T xi prime T xj prime T. So that is the same as the inner product, Euclidean inner product, g of gamma T into gamma tilde prime T, gamma tilde prime T. And now because this infimum of GVV over unit vectors is epsilon naught squared, that means this inner product here will be greater than or equal to epsilon naught squared into norm gamma tilde prime T squared. Okay. And so therefore I get that the length of gamma, this is greater than or equal to the integral from 0 to T naught of the norm of gamma prime. And the norm of gamma prime is greater than or equal to epsilon naught norm of gamma tilde prime. And by triangle inequality, the integral of the norm of gamma tilde prime is greater than or equal to the norm of gamma tilde T naught minus gamma tilde 0. And this norm is equal to 1, right? Because gamma tilde T naught belongs to the unit sphere, gamma tilde 0 is 0. So we get here epsilon naught. So therefore the length of gamma is greater than or equal to epsilon naught for all gamma. And so distance PQ is greater than or equal to epsilon naught. Is this okay?
Yes, sir.
Okay, so that proves that this distance function is a metric. Okay. All right, so let me. Okay. Okay, so any Riemannian manifold becomes a metric space, right? Where the distance between 2 points is the infimum of the lengths of piecewise C1 curves joining the 2 points. All right. So now our manifold has become a metric space. All right. So now there are two natural questions. We define the distance as the infimum of lengths of curves. So one natural question is this infimum realized? Right. So given 2 points in M, does there exist a shortest length curve? That means a curve whose length is equal to the infimum, the distance between P and Q. Okay. And the second question is, if such curves, shortest length curves exist, how do we characterize these length minimizing curves, right? Is there some way to characterize them? So, for example, we know in the Euclidean space, the answers to both these questions we know, right? The shortest length curves are straight lines. And, well, straight lines we can characterize as solutions of a second order differential equation, right? The second derivative is identically zero, right? So, what we want to do is generalize this to Riemannian manifolds. Okay. So, we'll see that at least locally we can find length minimizing curves. Locally they will exist. And these will also be characterized as solutions of a second order differential equation. And these length minimizing, well, locally length minimizing curves will be called geodesics. Okay. So we're going to talk about geodesics, but first, let me make one remark, which is an easy thing to see, that any smooth manifold admits a Riemannian metric. Okay. So this is not hard to see. If any smooth manifold admits a Riemannian metric. So for this, you use a partition of unity argument. Okay. So you take a cover by charts ui phi I, such that ui is a locally finite cover of n. So then I can take a partition of unity psi I, which is subordinate to the cover ui. Okay. Now you let G naught be the standard Euclidean metric on Rn. All right. The usual inner product on Rn. And what I can do is on each chart ui, I can pull back the Euclidean metric by the diffeomorphism phi I, right? Okay. Yes, I can pull back G naught by phi I. And then this is only defined on ui, but then I multiply it by this bump function psi I. All right. Psi I has compact support contained in ui. So then psi I times this phi I star G naught, this vanishes outside ui. So this is globally defined on M. Is this clear? And then I sum over I. Okay. And this sum is well defined because it's locally finite, right? Since I have a locally finite cover, only finitely many terms will be non-zero here at any point. Is this clear?
Yes.
Yes.
Okay. And so it's clear that this will be a smooth two tensor on M, right? And this is also symmetric. All I have to check is the positive definiteness, right? I just have to check this is positive definite at each point. And that's easy. That's because if I take any point P, then because psi I is a partition of unity, one of the psi i's is positive at P, right? And so therefore, GP of V comma V, this will be greater than or equal to. So note that all of these terms here, when applied to V comma V, these will be non-negative. So GP of V comma V will be greater than or equal to just this single term, psi I of P into phi I star G naught of VV. And this is positive because psi I of P is positive. All right. Is this clear?
Yes, sir.
Yes.
All right. So this G will be positive definite at all points. So this will be a Riemannian metric. Okay. So just by a partition of unity argument, any smooth manifold has a smooth Riemannian metric. Okay. I should make one remark. It's not clear whether you can get a analytic real Riemannian metric on an analytic manifold, a real analytic manifold, right? Because there you can't use a partition of unity. Do you understand?
Yes, because we can't have partial unity by analytic functions.
Right. You can't have a partition of unity with real analytic functions, right? So it's not clear that you always have a real analytic metric, but you always have a smooth Riemannian metric. Okay. All right. Okay. So now to motivate our answers to these two questions here about length minimizing curves, we're going to look at an example, which is the example of submanifolds of Rn. Okay. So submanifolds of Rn, we'll see these are naturally Riemannian manifolds. Okay. So okay. So what is a submanifold of Rn? So here n is a capital N. So a subset M of R capital N is called a little n dimensional submanifold of R capital N if the following holds. So there is a family ui comma phi I such that each ui is an open subset of R capital N and M is contained in the union of the ui's. Okay, so the ui's are open sets in R capital N, all right? And M is contained in the union of them. And for each I, phi I is a smooth diffeomorphism from the open set ui of Rn to some open set vi in Rn, such that phi I maps ui intersect M to vi intersect Rn cross 0. Okay. So maybe I should draw you a picture. So for example, S2, this is a two-dimensional submanifold of R3. So what that means is if I take a point here, then I have a ball in R3. Okay, so this is an open set in R3. This is my ui. And I have a diffeomorphism phi I. Which straightens out the manifold. So what that means is this is going to map to some other open subset in R3. So ui is an open subset in R capital N. This maps to vi, which is again an open subset of R capital N. And ui intersect M, all right, the part of the sphere inside this ball maps to the part of a plane inside this ball here. Okay, so this will be yeah, so I mean, so this sort of cap here, this is ui intersect M, and this here, this is Vi intersect Rn cross 0. Is the picture clear?
Yes, sir.
Okay, so I can straighten out the manifold at near each point. So this will give me charts basically, right? Because this is identified with a open subset in Rn. Is it clear?
Yes, sir.
Okay. So if I take pi to be the projection from Rn to R little n, okay. So then, so x1 to x capital N goes to x1 to x little n. Okay. Then what is my chart on M? The chart will be phi I tilde, which will be pi composed with phi I restricted to ui intersect n, right? So this goes from ui intersect n. So let me call this ui tilde. This is an open subset of M. This goes homeomorphically to some Vi tilde, which is an open subset in Rn. All right. Is this okay?
Yes.
Okay. So this gives me charts on M, and if I look at the change of charts, so all right. So this is say M, this curved thing, and this is my ball in R capital N. And if I have two charts, phi and a psi. So these are diffeomorphisms to balls in R capital N. Okay. So this is a diffeomorphism. This is a diffeomorphism. So these map to planes intersect balls. And then I'm taking the projection to get an open set in R little n. So this will be some V tilde, which is open in R little n. This will be a W tilde, which is open in R little n. So then this is my change of charts, right? And this change of charts is the same as just I take this smooth map here, right? Say F equal to psi composed phi inverse. So this is a diffeomorphism from the ball to the ball. And then I just restrict it to the part of the plane inside the ball. So this map is smooth from here to here, right? From the plane to the plane, this is a diffeomorphism. So therefore, over here, this map will also be a diffeomorphism. All right. This F tilde will be psi tilde composed with pi tilde inverse. Is this clear?
Yes.
Okay. So therefore, N with the charts ui tilde pi I tilde this is an N manifold. Okay. All right. So submanifolds are of Rn are also manifolds. And according to our earlier definition. And now, if you look at this picture, if I take a point here, then for a submanifold of Rn, the tangent space should be identified with a subspace of R capital N, right? So how do I do that? Well, like this. So let me take phi I. This is my diffeomorphism from R capital N to R capital N. So this has coordinates x1 to x capital N on ui, say. So let me take a point P in here in this ui intersect N, all right? And let I be the inclusion from M into Rn. Okay, let this be the inclusion map. And so let phi I tilde. So this is x1 to x little n. This is my chart on ui tilde, right? The first little n coordinates give me my chart. Yes. Okay. So then what you can see is that the derivative of this inclusion map. So M is a smooth manifold, right? So this I will be a smooth map sending the tangent space TPM to the tangent space of R capital N, which is identified with Rn. This will be one-to-one because we can define a retraction from this this ball ui into just the part of ui inside M. So this ui tilde is ui intersect M. So how do I define a retraction? Well, I have a retraction here, right? Onto this plane is just the usual projection, right? The projection pi. So I conjugate the projection pi here by this diffeomorphism phi I. That will give me a retraction from this ball to this ui intersect M, right? So my pi tilde, this retraction will be phi I inverse pi phi I. This goes from ui to ui tilde. And clearly, pi I tilde composed with I, the inclusion, is equal to the identity of ui tilde, right? If I start with a point here, then it stays fixed under pi tilde, right? Is that clear?
Yes, sir.
So now if by the chain rule, I just take derivatives on both sides. So I get that d of pi tilde composed with dip. This is equal to the identity of TPM. So that means that dip will be one-to-one, right? Is that okay?
Yes.
Okay, so therefore I can identify for a submanifold of Rn, the tangent space I can identify with a subspace of Rn. All right. So therefore, we can identify TPM with a subspace of capital R power capital N. And now we can restrict the Euclidean inner product on R capital N. We can restrict this to TPM. And this will give an inner product GP on TPM, right? I'm just restricting an inner product to a subspace. So it's going to stay an inner product, right? Okay. So what I need to check is that this inner product depends smoothly on P. P is a point in M, right? I have to check that this defines a smooth Riemannian metric on M, okay? So how do we see the smoothness? Well, note that my basis of the tangent space, TPM, is given by these del del xj's. What are these? These are going to be d phi I tilde inverse of EJ, right? Yeah, because I mean d phi I tilde maps del del xj to EJ, right? So del del xj is just d phi I tilde inverse of EJ. Yes? Okay.
Yes, sir.
Right. So what is my what are the coefficients of my Riemannian of my metric? GKJ at a point P is going to be the Euclidean inner product between d phi I tilde inverse at the point phi I tilde of P applied to EK and d phi I tilde inverse at the point phi I tilde of P applied to EJ. Okay. And here, this as a function of P, this is going to be smooth because phi I tilde, this is my chart. This is phi I tilde of P is a smooth function of P. And phi I tilde inverse, where does that go? So phi I tilde inverse is going to go from this R little n here into R capital N, right? It's going to be a smooth map into R capital N. So its derivative is smooth. Okay. And so this d phi I tilde inverse depends smoothly on this phi I tilde of P. And so the whole thing is smooth. Is it clear?
Yes, sir.
Okay. So therefore we get a smooth Riemannian metric on M. This is called the induced metric. Okay. So any submanifold of Rn is naturally a Riemannian manifold with the induced metric. Okay. So, I mean, I've done this a bit formally, but in the picture, it's clear what is happening, right? You just take any submanifold, you draw your submanifold, and the tangent space at any point, you know, is naturally identified with a subspace of Rn. And I'm just restricting my Euclidean metric to this tangent space. Okay, so if I take a curve in the manifold, that's a map gamma from an interval AB into the manifold. So here, if I take a curve, gamma. So then gamma goes from where? From AB into M, and this is sitting inside R capital N. So this is just a usual C1 curve in R capital N. Okay. And the length of gamma is just the integral of the usual Euclidean length of gamma prime. Okay. This is the usual Euclidean norm of gamma prime. Okay. So my tangent vectors are just vectors in Rn. I'm just taking their vectors in Rn, I'm taking their usual Euclidean length and integrating. Okay. Fine. Okay. Now I want to come to what are going to be shortest curves in a submanifold of Rn with the induced metric. What are shortest curves going to look like? Okay. So first what we can do is we can decompose, since TPM is a subspace of Rn, I can decompose R capital N as the direct sum of TPM and its orthogonal complement, right? So let me write any vector V in R capital N as a tangential component Vt plus a normal component Vn. Okay. So Vt here belongs to TPM and Vn belongs to TPM perp. Okay. So in this picture, if I take a vector here, V, so then there's a tangential component and then there's a normal component. Okay, so this will be, this is the tangential component Vt and this is the normal component Vn, all right? Is this okay? I'm breaking up any vector into a tangential and a normal component, all right? Okay. Now, suppose that gamma is a curve in M which is length minimizing, all right? Suppose gamma is a length minimizing curve from P to Q, which are points in M. Gamma is a curve in M of shortest length. So then we can do what people do in the calculus of variations. You consider a variation of this curve gamma, okay? So say say this is my shortest curve. Okay. Say this is my shortest curve. Now what I can do is I can consider variations of this curve. That means one parameter families of curves which contain gamma, all right? So something like this. Okay, I can consider a one parameter family of curves. Yes. Okay.
Yes.
So that gamma naught is equal to gamma. Okay. So then if I look at the function, t goes to length of gamma t. Okay. let me assume that this function is differentiable in t. Okay, so this will be true if I take a smooth variation. Then this has a minimum at t equal to 0 because gamma is length minimizing. So ddt at t equal to 0 of length of gamma t therefore has to be equal to 0 because it has a minimum at t equal to 0, right? Yes?
Yes, sir.
Okay. So this is what we're going to do, just basic calculus. So, but we're going to make some simplifications. So, all right. So my one parameter family of curves is going to be a map f from an interval minus epsilon comma epsilon cross AB into M, a smooth map such that for all s in the interval minus epsilon epsilon, the curve f of st starts at P and ends at Q. So all of these curves start and end at P and Q. And f of 0 comma t at when s is 0, then I get the curve gamma t. So I let gamma s of t be f of s comma t. So gamma s is a curve joining P to Q. And what I can do is I can look at what's called the variation vector field, V of t. So this is going to be del del s at s equal to 0 of gamma s of t. Okay, so in this picture, I differentiate with respect to the s parameter. Okay, so for example, I mean, I'll get a vector field then along this curve, gamma, which maybe looks something like this, okay? And this vector field, because the endpoints are fixed, this vector field has to vanish at the endpoints, right? Okay. All right. So I get this variation vector field. So at each point, this V of t is a vector in the tangent space to M at gamma t. Okay. Now, suppose for simplicity that gamma is a C2 curve. And since length is invariant under reparametrization, we can also assume that the length of gamma is constant, equal to C, say, right? Okay. We can always reparameterize a curve to have constant length, all right? Okay. So now note that ddt of this inner product between Vt and gamma prime t, this is going to be what? By the product rule, it's V prime t gamma prime t plus Vt gamma double prime t. Okay, fine. Now we have that the length of gamma is less than or equal to length of gamma s for all s, and you have equality at s equal to 0. In other words, this function has a minimum when s is equal to 0. So we differentiate and we get 0 is equal to dds at s equal to 0 of length of gamma s. So this is dds at s equal to 0, integral a to b, inner product gamma s prime to the power half dt. So, so I differentiate this with respect to s. So I'll get a half coming down, and then I'll get this to the power minus half at s equal to 0. So that will be basically 1 over the norm of gamma prime, right? So that will give me a 1 over c, okay? And then I'll get 2 times del del s at s equal to 0 of this gamma s prime t. So gamma s prime t is del f del t. This inner product with gamma prime t dt. Is this okay?
Yes, sir.
Yes, sir.
Okay. Now what do? This I interchange del del s and del del t. So this becomes del del T of del F del S. But del F del S is V, my variation vector field. So, and I have a del del T outside. So this will become inner product of V prime T with gamma prime T. Okay? Yes? Now,
Yes.
this V prime T, gamma prime T, I use this this formula here. I write this as ddt of Vt gamma prime T minus inner product Vt gamma double prime T. Okay. So I get 1 over C into this. So ddt of V gamma prime minus inner product V gamma double prime. And so this I can integrate by the fundamental theorem of calculus. And so this term will disappear because V vanishes at A and B, right? V vanishes at the endpoints. So this term vanishes. So finally you get minus 1 over C integral A to B V gamma double prime, okay? And V is tangent to the, V lies in the tangent space to M. So therefore the inner product with gamma double prime is the same as the inner product with the tangential component of gamma double prime, right? Yes? Because V lies in the tangent space. So the inner product with the normal component is 0. So only the tangential component remains, right? So
Right.
finally, what do we get that the integral A to B of V with the tangential component of gamma double prime, this is 0 for all variational vector fields V, right?
Right.
And therefore, basically the V plays the role of test functions. Since this is true for all V, it follows that gamma double prime tangential component has to be identically 0. Okay. And this is called the geodesic equation for M. So this shows that the length minimizing curves satisfy this second order differential equation. Okay. So we'll talk more about this next time. We're out of time. Okay. So let me stop here. All right. Okay.
Okay.
Okay. All right. So see you Thursday.
Yes.